Hey everyone, welcome to the post-contest discussion for Leetcode Biweekly 149. Sorry for the technical issues. Okay, so firstly, I would like to give a quick shout out to the CP31 sheet. The new CP31 sheet is live, and basically CP31 is a set of 31 handpicked problems and different rating ranges. So new rating ranges have been added, and the new CP31 sheet is live. Do check it out on TLEeliminators.com/CP sheet. Yeah. Will question 4 be discussed? Yeah, we'll be discussing question number 4. Now, we are given a string. So let's move to the first problem. And the first problem, define valid pair of adjacent digits in string. We're given a string S consisting only of digits. A valid pair is defined as two adjacent digits in S, such that the first digit is not equal to the second, and each digit in pair S uh, appears exactly as many times as the numeric value. And we had to return the first valid pair in S. So let's look at what this problem says. Let's start in the non-increasing order. Right. Actually, for the question 4, we'll be discussing the idea. For implementation, I've been facing some bugs. So yeah, we'll be discussing the overall idea for the question 4. Implementation part, I will be sharing later. Now, for the question 4, question 1, let's look at the first sample test case. It is 2523533, and according to the question, so basically in the question we had said that we had to find the first valid pair of the first valid pair, and what the defined valid pair was that the first thing that for any pair its two digits, like two of its members, should not be equal. All right, so 2 should not be equal to 5. And the later thing was that these two digits should be valid in the sense that if you're taking a 2, then the number of 2's in the string should equal to 2. So 2 can be a part of the pair if the number of occurrences of 2 in the string is equal to 2, and 5 can be valid if number of occurrences of 5 is equal to 5. So consider the string 2523533. So if you look at 253533, sorry, 2523533. Now 2 occurs 1 and 2 times. So you could have 2 as a part because number of occurrences of 2 is equal to 2. Then 3 occurs 1, 2, and 3 times. So number of occurrences of 3 is equal to 3. So even it's good to have 3, 2 in the pair. So it won't be a problem. But 5 occur once and twice. So the number of occurrences of 5 is equal to 2, which is not equal to 5. So you can't have 5 in a pair and say that it's a good pair. Basically, let's look at all the pairs. So 2, 5, 5 is not good, so this pair can't be good. 5, 2, again 5 is not good. And 2, 3, 2 is good, 3 is good, and 2 is not equal to 3. So 2, 3 is the first good pair that we have found, and basically I had to return this pair. All right, so yeah, that was the basic. This was what we had to do in this problem, and over here you would return 2, 3, and similarly for this one. So let's take the second test case just to be clear where things won't work out. So over here, 2 occurs twice, like 1 and 2. 1 occurs once. So number of occurrences of 2 equal to 2, so 2 can be part of pair. Number of occurrences of 1 equal to 1, so 1 can be a part of pair. Look at the first pair. What are its two members? 2 and 2, but 2 is equal to 2, and according to problem we want both of these things to be different, so this can't be the case. Then look at the second pair, 2 and 1. and like 2 is valid, 1 is valid, and both of these are different, so it's a good pair. And the first pair we have found is 2 1. Similarly, and in the case that you don't find any pair such as this, then you just return an empty string. There are right. Now let's look like how you would implement this thing. First, what you could do is what we did over here, like intuitively, we just first look which digits are valid and which are not valid. There, in the code, what we can do is you can maintain an array of 9 size 10, like 0 1 2 all the way up to 9, and for each we see, okay, is this digit good? We basically count the number of occurrences of this digit in the string and say, is it equal to this digit? If it is, then this is a good digit. If it's not, then it's not a good digit, so it will value true or false. Then we can iterate over all the possible pairs, like I equal to 0 1 1 2 2 3, so on and so forth. Check if the two digits are not equal, and if the first and second digits are good. If they are, then you basically return the substring starting at I and 2, basically the pair I and I plus 1. Otherwise, we return an empty string. That was the first question. I've been doing half an year. Oh, we'll see about those questions later. For now, let's focus on questions. So that was the first question. Let's move to the second question. The second question was reschedule meetings for maximum free time. Actually, question 2, B and C were very similar. Now, in this question, you are given an integer event time denoting the duration of an event, where the event occurs from time t equal to 0 to event time. And we're also given two arrays, start time and end time, each of length n. And these basically represented the start and end time of n overlapping meetings. And each of these meetings occurred in the event time, that is 0 to event time. So the ith meeting occurred between start and end time. And we had the option to reschedule at most k of these meeting by moving their start time while maintaining the same duration. So you couldn't change the duration of the meeting. So if the meeting was going on for 2 hours, it had to go on for 2 hours, but you could move the start time to somewhere else. And we had to move k such meetings such that the longest continuous free time during the event was maximized. And we had to return what this maximum time was going to be. Also, in this question, like in B question, the relative order of all meetings should stay the same. We'll look at what this means when we go over the examples. And we at the end we had to return the maximum free time possible after rearranging the meetings. Free time was basically time where there was no meeting occurring. Now let's look at the example. Let's look at the example. The first example was event time is 5, and these were the meeting times. So all right. So the first example is, this is 0, this is 5. So basically here it was given that the event time was 5. So you have 1, 2, 3, 4, and 5 slots where the event is going on, and all the meetings had to lie in these slots basically. Now our test case said that the first meeting started at 1 and ended at 2. So the first meeting starts at time t equal to 1 and ends at time t equal to 2. And the second meeting starts at 3, ends at 5. Starts at 3 and it ends at 5. And what we can do is we can move exactly one meeting, that is k equal to 1 meeting, to basically we can move its start time to somewhere else. And we are given like one thing we were given in the question was that these meetings are non-overlapping. So you won't have a meeting which starts at 1, ends at 3, and another meeting which starts at 2 and ends at 4. This would never happen. So your meetings would always be overlapping. And you also have to ensure that after you move your meetings around, this property remains, that the meetings remain overlapping. So basically, in this case, you could move exactly one meeting and you have to maximize the free time. So what is free time? These are the slots occupied by meetings, and whatever remains in between, like 0 to 1, there's no meeting over here. 2 to 3, there's no meeting over here. So these are the free slots, and we had to maximize the maximum continuous free slot. So this is one continuous free slot, this has length of 1. This is one continuous free slot, this has length of 1. The maximum of these two is 1. Now you have choice to move these meetings around, exactly one meeting around. Now what you can do is, let's just say that this meeting starts at time t equal to 1, the first meeting, and ends at time t equal to 2. You move this meeting to start at, basically you move this meeting to the right by 1, and what you said was, this is 0, 1, 2, 3, 4, and 5. And yeah, the one of the meetings was between 3 to 5. So this was the meeting number 2. And the meeting number 1, what you say was, okay, this started at 1 and ended at 2. So the duration of this meeting was 1. You couldn't change the duration, but you can change the start time. So you change the start time from 1 to 2. Now this meeting number 1 starts at 2 and ends at 3. So this is your meeting number 1. This is your meeting number 2. Now what this did was, this basically merged these two free slots. So these two free slots that you had, now it is a free slot of length 2. So now your free slot size has increased, and the maximum continuous free slot has size of 2. Your answer would be 2 in this case. 2 as it's over here. All right. Now let's just go over this second test case for once, and we'll basically, like, finally we'll just see what's the main idea behind solving this problem. This is like the test case 2 of this problem. Over here, the event time was given to be 10. So you had slots starting at, like, at most 0 and between 0 to 10. So this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and finally 10. And your meetings were between 0 to 1. So the first meeting started at 0, ended at 1. This was your first meeting. Second meeting was between 2 to 4. So it started at 2, ended at 4. And the last meeting was between 9 to 10. So this was your third meeting. And your free slots, if you look at it, you have a free slot of size 1 over here, and you have free slot of size 1, 2, 3, 4, and 5 over here. Okay. Now, what you could do in this case is, you could just say that you're going to, there are a few things you could do. You could either shift this to over here, like you could shift the start time of 2 from 2 to 1, then even its end time would shift to right by 1. Or you could shift this to up to here, like you could basically have it this to such that it ends at exactly before 3 starts. But there's one thing you can't do, that basically you can't just pick 3 and put it in between somewhere over here. So our problem said that we had to maintain the ordering of meetings. So if 1 starts first, ends first, then 2 starts and ends, then 3 starts and ends, then we could move the start time of 2, 3, 1, 2, 3, whatever k number of meetings that you have, such that 2 can start somewhere over here, end somewhere over here, or start somewhere over here, end somewhere over here. But at the end, 1 starts first, then 2, and then 3. This order should remain according to our question. So in this case, what you could do is, one of the possibilities is, this is 0, this is 10. One of the possible things that we could do is, 1 is between 0 to 1. This is the first meeting. Then you could have between, this was 2 to 4. So you could start 2 at 1 to 3. So this could be second meeting. And the last meeting could be between 9 to 10. And since k equal to 1, we can only shift exactly one meeting. If k was 2, then you would also have, like, you couldn't do any better over here. But yeah, like k is exactly 1 over here. So you shift one meeting. And between 3 to 9, you get 5 as, sorry, not 5, but 6 as your like free slot size. 9 minus 3 is equal to 6. So you get a free slot of size 6. So the maximum continuous free slot size is 6, and your answer would become 6. Right? So, and now, how do you approach this thing? Also, like one thing that I hope that it's clear over here, that if this is the meeting 1, this is the meeting 2, and this is the meeting 3, this is like according to timeline. You can shift 2 over here or 2 over here, but you can't just say that 2 will occur after 3. This can't happen according to our constraint over here, which says that the meetings cannot be rescheduled. Sorry, not this. Yeah, the relative order of all meetings should stay the same. So that is, even after you reschedule your meetings, one should occur first, then 2, and then 3. This is in the case of problem 2. In problem 3, this will change. Now, observe one thing. All right. So now, like, what is the idea that you could use to solve this problem? If you try to basically go on, like, what happens when you move a meeting? So over here, we moved the meeting number 2. All right. So what happened when we moved meeting number 2? So you had a meeting number 1 over here. Then you had a free slot over here of size 1. Then you had a meeting number 2. Meeting number 1, I guess it had size of some, it had size of 1 and some 3. So, and in between them again, you had a free slot of size 5. And then you had your meeting number 3. Now, what we did was we moved the meeting number 2 to the left. You could have also moved it to the right. But what happened when you moved your second meeting? Well, basically, when you moved your second meeting, so when you moved your second meeting, it merged these two free slots. So if you look at what our timeline looks after moving the second meeting, this is your meeting 1, this is your meeting 2, and after you move your second meeting, both your free slots have been merged. Okay. So this is basically what happens when you move your one of the meetings. Now, we want to maximize this size of the biggest free slot. Basically, that the biggest free slot is the longest running free slot. That is like longest amount of time that there are no meetings, consecutive no meetings. And we want to maximize this free slot. Now, how do we do that? Now look at one thing. If you have a meeting here, then meeting here, and then a meeting here, then a meeting here, and then a meeting here. And let's just say you have, then obviously in between you would have free slots, and you have some free slots. Now, if you move this meeting, so let's just say you move this meeting somehow, and that merges these two free slots, and then you move this meeting, it merges these two free slots. It's basically unoptimal because there's this meeting in between that's going to divide these two things. So even after you merge these two free slots, you're going to get one big free slot over here and one big free slot over here, but these two are going to be separate. Rather than that, it's always optimal that you move consecutive meetings. So what do I mean by moving consecutive meetings? So if you have a meeting over here, 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 you have a few meetings over here, and you look at the free slots. If you can move two meetings, then rather than moving this meeting, leaving one meeting and moving this meeting, it's always optimal to move two consecutive meetings, and that will lead to, so you can move this meeting over here and like basically stick these together, and this maybe you can move it to the left or right, stick it over here, and that would basically merge these three free slots. All right. So basically, by moving your meetings, what you're doing is you are kind of merging your free slots. So yeah, basically like that's the core idea for this problem. Moving k meetings. Like, so moving k meetings, consecutive meetings, you can merge k+1 free slots. And then like once you have this idea, what you can do is you can just go over all the like this is actually there would be a free slot at the start and end too. So that would be sort of like there's a free slot starting at 0 and up to this start time, and a free slot over here up to this point in time. Then what you can do is you can just iterate over all the possible windows of k+1 free slots and see what's the maximum of them, like maximum amongst them, and that would be your answer. All right. So this was the first, and this is the second. So this is like the code for the second. So you have this vector of n free slots. Initially, your free slot is 0 to the start time of the first meeting. Then you iterate over all the meetings. Like this is the free slot that I-1 meeting would end over here, and ith meeting would start over here. That would be this free slot. And yeah, like you have basically n+1 free slots. Then you just merge the first k plus what is the time that you would get by merging the first k+1 free slots. That is, you set it to your current free time and you set it to your max free time. Then you basically like this is basically sort of a sliding window where you add a free slot in the front, remove like the free slot at the back, and you have k+1 consecutive free slots, and you like basically update your maximum, like your answer, the maximum free time you could have with this, and finally you just return it. So that was the second one. All right. Now let's move to the third question. All right. So the third question said that the third question was also reschedule meetings with maximum free time. So this was similar to the second question. In this, we were given an integer event time, same as previous time. We had this event time, and we were given the duration of event, and we again had n meetings, each with a start time and end time. And over here too, the n meetings were non-overlapping, and all of them had to lie between this time t equal to 0 to event time. And the ith meeting basically occurred between start and end time. Now over here, but previously we could reschedule at most k meetings, but here we could schedule at most one meeting. So we could only move at most one meeting. And again, after moving the meetings had to remain non-overlapping, and we had to find the maximum longest continuous period of free time, basically the maximum free slot that we saw in the last problem. And we had to return this maximum amount of free time, continuous free time. But in this case, there was no constraint on the relative ordering of the meeting. So previously we had to maintain that if this meeting occurred first, this meeting occurred second, then third, even after our rescheduling, meetings had to occur in the order 1, 2, 3. That could not change in the previous problem, but in this problem, it could change. So let's look at a problem. So I guess the first test case is very similar to the previous one, so I won't go over it. Over here, you have 1, 2, and 3 to 5 meetings. So you could basically just put this 1 to 2 meeting to the left or right, and that would give you a free slot of size 2. Let's look at the second test case. That would be like more representative of what's different in this problem. So we are discussing problem C, the third problem. All right. And your event time starts at 0 and at 10. You have 0, 1, 2, 3, 4, 5, 6, 9, and 10. All right. So we had 3 meetings in this case. First meeting started at 0, ended at 1. So this was your meeting number 1. This was the second meeting was between 7 to 8, your meeting number 2. And your final meeting was between 9 to 10, your meeting number 3. All right. And what you could do now in this case, like up to this point, you only had one choice. Like you could, if you wanted to move meeting 2, you could move it to here or move it to here. If you wanted to move meeting 1, you could move your meeting 1, and if this was your meeting 2, you could only move it up to this point, but you couldn't cross meeting 2. But now what you can do in this problem is, like in the third problem, is you have a choice basically take your meeting 2, like this is your meeting 2, this is your meeting 3, and this is your meeting 1. You can basically take your meeting 1 and put it between 2 and 3, as long as there's space. So as long as there is enough space, you could just take your meeting 2 and move it over here. There's no need to worry about ordering, will meeting 2 occur first or meeting 2 occur second. And yeah, like according to this test case, what you could do is you could just take this meeting to move it over here. Then your meetings would look like you start at 0, you end at 10, and your meeting 2 would occur between 7 to 8 would be meeting 2, 8 to 9 would be meeting 1, and 9 to 10 would be meeting 3. And this would be your free time. So 0 to 7 would be your free time, and your answer would be 7. So that would be your answer. Go to the third test case. Oh yeah, right. There's 3 test cases over here. All right. This test case would like explain it better, I guess. If you look at this test case, here you have event time of 10. So this is between 0 to 10. You have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And the first would be like 0 to 1. This is your first meeting. Then 3 to 4 is your second meeting. Then 7 to 8 is your third meeting, and 9 to 10 is your final meeting. Now, in the second test case, you weren't allowed to, like, if you wanted to move this to, you can move at most one meeting in this problem. You can't move k or anything. But even in the second problem, if you wanted to move this to, you could all at most take it up to here or take it up to here. That was the max you could do. But in this problem, you're basically allowed to take this 2 and put in between this 3 and 5. So you don't have to move it linearly. Like you can get rid of the ordering. There's no need to worry about that. So in this case, like your answer would be, you have your 1 over here, it ends at 1, and this is your 3. You could fit your 2 over here, and you could fit 5 over here, and our line would look like this is 10, 3 starts at 7, and you have basically this is the free time you have in between. So there are 6 units of free time, like 6 units of continuous free time. But if you are only able to move 2 to the left or right according to the second problem, you would have at most 5 units of free time. So that's the different thing about this problem. It would be 6 over here, right? Now, this is like the problem statement of the third one. And now, how would you solve this thing? What we did in the previous problem, that won't apply over here. So in the previous problem, we just said that whenever you move a meeting, you're merging 2 consecutive free slots. But that doesn't hold over here, because if you are moving a meeting, previously you were either moving this meeting to basically kind of attach to this meeting. So that was merging these 2 free slots, or you are moving it to attach to the left of its meeting. Now, it may also happen over here. Like, what's the extra case that can happen over here? Something that can happen over here is you have these meetings and you have these free slots. And let's say you have decided to move this meeting. Now, if you move this meeting, like say to the right or to the left, that would just merge these 2 slots. But if it's possible, if there's enough space, you could also move this meeting to this free slot. And then you're kind of getting a free slot of this meeting size for free. And like you're getting an additional free slot of this meeting size. And that would be like an extra move on your side. So how do you account for this? Okay. Now, just look at when can you do this operation. So like, how do you account for this? In the previous operation, it was very clear. Whenever we move a meeting, it just merges the previous and the next free slot, and we just iterated over all the windows and merged those free slots and had their answer. Now in this case, you can move your meeting to some other free slot, and we can move at most one meeting. So how do you like account for this type of operation? What you can do is, let's look when can we move a meeting in that manner. So these are your free slots. So when can you move this meeting, like basically out of these two free slot boundary? Okay, if you want to move this meeting out of this free slot boundary, like to somewhere else, then you need some free slot which is going to accommodate this meeting. So if, let's just say, this meeting has a size of 2, like this is its start time, if it is s, then its end time is s plus 2, then this meeting has size of 2. If you want to move it to some other free slot, then that free slot has to have a size greater than equal to 2. So if there's a free slot of size greater than equal to 2, then you can move this meeting out of this, and you basically get this like free slot 1 plus the meeting wherever meeting was being conducted, that slot becomes free. That's a slot of size 2, and the third free slot. So you're basically getting 3 free slots. That would be that would be possible in this case. Now, when can this happen? This can happen when, if you leave out these two free slots, whatever remaining slots there are there any slots that can accommodate this meeting? If you look at that condition, like if there's any slot that can accommodate this meeting other than these two slots, then you can just take this meeting out and put it into that slot, and you'd get this free slot plus these two free slots. So that would be like how you could kind of simulate this new action, like this new action that you can do, because you don't need the ordering of meetings anymore. So what you can do is, we can just go over all the meetings. For each meeting, we can see, okay, I'm considering this meeting. What happens when I move this meeting? Well, first thing, that it merges these two slots, so that at least that's going to be my answer. Like f1 plus f2 is at least going to be my answer. Other than that, is there anything else that I can do? Like, is there some way in which I can move this meeting out of this place? In that case, we have to look, okay, other than these f1 and f2, whatever the remaining free slots there are, is there any slot that can accommodate this meeting? If the slot can accommodate this meeting, then your answer is basically f1 plus f2 plus the size of meeting. Else your answer, even after moving that meeting, you're at most going to get f1 plus f2 size free slot. And you can just do this for every other slot. Now, how do you get if there's any other slot which can accommodate this meeting? To do that, what we can basically do is, you can maintain a prefix maximum and a suffix maximum for the free slots. So these are your meetings. You can maintain a prefix and suffix maximum for your free slots. So basically, if this is the meeting that you're trying to see, can I move this meeting to the to somewhere else other than these two free slots? And you can check what in the free slots that are to the right of this meeting. So that would be your suffix maximum. What is the maximum size of free slot? And that would be given by your suffix max of free slots. And to the left, whatever meetings there are, what is the maximum free slot to the left? That would be your prefix maximum. And you can see, like, is there anything that can accommodate this meeting? If it is, then you'll get an extra 1 plus s. Prefix and suffix. Not some, but prefix and suffix maximum, because some won't, like, basically you can't split your meeting into 2 or 3 slots. You need exactly that size slot. In this problem, like if you look at the implementation for this problem, first see what is the number of meetings that you have. Then the meeting time, we just see, like, okay, we calculate the meeting time for each meeting, that is end time minus start time. Then again, you calculate the free slot as you did in the previous problem. The first meeting, like the first free slot is between 0 to the start of first meeting, Then each consecutive free slot is between the start of the next meeting and the end of the current meeting. And finally, you have a finals free slot that is like end of the complete line and the end of last meeting. And again, you maintain this maximum free time variable. Now over here, you're moving one meeting. So whatever operation you had previously, basically moving the meeting to extreme left or extreme right, that would still merge to consecutive free slots. So you still need to iterate over all the meetings and see what would be the result of merging two consecutive free slots. You can update your answer with that, your max free time. Then we just basically maintain, we create a prefix and suffix array for our free slots array. That would be this thing, like prefix of I is maximum prefix of I minus 1, suffix of I is maximum suffix of I plus 1. Basically, suffix of I would store what is the maximum free slot that starts at, like, that is I or after I, and prefix of I would store what is the maximum free slot that is at I or prior to I. Then we try to move the, we iterate over all the meetings 0 to n and try to see, can I take out the ith meeting and move it somewhere else such that we get the free slot, like the wherever meeting occurred, that becomes a free slot and it merges with the adjacent free slots. We can do that when, basically this is the check function. We can do that if there's some free slot previous to I minus 1 which has size of at least this meet time size. In that case, you can just move your free slot back. Basically, the first condition would refer to, you have your meet is over here. So we want this. Yeah, the first condition would basically refer to, this is the meet you are considering, and there's some free slot over here that is big enough to accommodate it. Then you push your your meeting over here. That would be this thing, like prefix of I minus 1 is greater than equal to meet time. And then this is your second condition, that suffix of I plus 2 is greater than equal to meet time, meaning that there's some free slot ahead over here, which is enough to accommodate this thing. If it is, then in that case, the answer you get is, one thing is free slot of I, then free slot of I plus 1, basically these two free slots, and the meeting time. Even this becomes free now because the meeting has moved out. So even this is a free time now. So all these three things combined make a one big free slot. So that's your like max free time, and you'd return this thing. All right, so that was the third problem. Now let's move to the final problem. For the final problem, like, I'll discuss the idea, but unfortunately it seems my implementation has gotten some bug and still like debugging it. So I'll share the like submission later, the implementation later. So right now, let's just go over the question and see what is, like, what are the different approaches you could see try over here. The fourth question was minimum cost good caption. And this, we are given a string caption of length n, and this string was called good if every character appears in groups of at least 3 consecutive occurrences. So what is a group of occurrences? Like basically AAA. So you have a block of A's, then you have a block of B's, like 3 B's, and each of these blocks had to have a size of at least 3. Now we were given an operation and we could perform it any number of times. In one operation, you could choose an index and change the character at that index to something else. What could that be? You could change the character to the previous character. So for example, if your character was B, then you could change it to C. If it was D, you could change it to C. Like basically one place back in the alphabet. But if it was A, then you can't operate in this way. Like you can't change A to Z as it usually is. A would always remain A. Or you could change the character to something that's after it. So A could become B, B could become C, or say D could become E. So these were two operations, like these were two things you could do in one operation. So, and our task was to given caption into a good caption using minimum number of operations. And if there were multiple possible captions that you could do in that minimum number of operations, then you have to return the lexicographically smallest one amongst them. And if it was impossible to do that, then you would return an empty string. And this was the definition of lexicographically smaller string. Basically, if the two strings, the first place where they differ, whichever string is has the smaller character is lexicographically smaller. Java code for the first problem. Yeah, I'll look at it after and share a link. So let's look at this test case. CDC. So not A. This is problem D. So we are looking at the fourth problem. So this was CDC. Our caption string was CDCD. Now, which, like, according to the problem, the caption is good if all consecutive block, like all blocks of equal characters have size of at least 3. But if you look over here, C is one block, it has size of 1. D is one block, it has size of 1. This has size of 1, and this has size of 1. So this is not a good string right now. Now, what we can do is you take this thing and in one operation, operate on this D. The operations we are available is that when you operate on D, you can either convert it to the previous character, that is C, or you can convert it to the next character, that is E. So you could say this is CCD. Now, this block, after this operation, this block has a size of 3. So this is a good block. But this block has size of 1. So it is not good. So you can once again operate on it, on make all of them equal to CCC. So this is like one good caption. But there was one more, like another possible way to do this thing. That would have been, you could convert this C to D. So your operation can take the character back or take it front. So you could say CDC becomes DDCD. Then you could once again operate on this C and then convert it to like C becomes D once again, DDD. So both of these pathways took 2 operations. This was the first operation. This was the second operation over here, converted D to C, D to C. In this, you had one operation and you had 2 operations. Both of these took 2 operations and it gave us these 2 strings. And according to our question, we had to find the lexicographically minimum ones amongst these 2. That would be our answer. So if you compare CCC and DDT, the first place where they differ is the first character itself. Here, C is smaller than D by our alphabetical order. A is smaller than B, then B is smaller than C, and so on. C is smaller than D, so our answer would be CC. This is the smallest thing that you could do get by doing 2 operations, and 2 is the minimum number of operations you'll need. So that was the first test case. For second test case, the second test case is similar to, so in the second test case, you have ACA, and what you can do is make one operation and convert this C to B, make one more operation and convert this B to A, and you have AAA. And in the final operation, like in the final test case, you have B, you are given B and C. And now no matter what you do, this string is going to have a size of at most 2 characters. But our problem said that a string is good if every block, like this is a block of A's, like block of same characters. Every block of same characters has a size of at least greater than equal to 3. But this string has size of 2, so there's nothing you can do over here. Like no matter what operations you do, this is always going to have a size of 2, which is strictly less than 3. So your answer would be empty string, because you can't, no matter what operations you do, you can't have all blocks to have size of at least 3, because there are only 2 characters. That was our problem. Now, what can you do? Like first thing, let's look at the constraints for this problem. All right. Up to this point, like the constraints were not all that what we had to look at, because we are looking at O(n) solutions. Now, if you look at the constraints for this problem, the caption length, let's just say it's n, that's up to 5 times 10 raised to power 4. Okay. What is 5 times 10 raised to power 4? Well, you won't get a O(n) squared solution in this, like an O(n) squared solution won't pass in this case, because 5 5 is 25. So you would have 2.5 into 10 raised to power 9 type of complexity over here. So that would definitely lead to a TLE. But you could have O of n into something that's pretty big, like something that's up to 10 raised to power 3 in this thing. So first thing is that even if you have something that's a bit heavy in each iteration, that would work. But you can't have something like an O of n squared solution. Okay, that was like on the constraint side of things. Now let's look at what we are doing. So what we have first, like what are the observations that we have? First is that your block size has to be greater than equal to 3. All right. What does this mean is that if your block size has to be greater than equal to 3, so whichever string you pick, this kind of unties like what are the possibilities that you have for each character. So let's say that you're making your string, so you are given some caption, and you're basically like you started at the first character, you made the first character into A, then you went to the next character, you made it into an A, you made it into an A, you made it into an A, and then at the next character you decided to start making them into B, like whatever you wanted to have minimum number of operations and all those things. Now the thing is, you went on making these things into B. To make the next character, like you either make the next character into B so that it continues this block of B's, or you make it into something else. All right. But whatever you do, this A's don't matter. Like these A's don't matter. The only thing that matters is, are you going to extend this block of B's or are you going to start a new block? That's the only thing that matters over here. uh, what which blocks came prior to this don't matter. We'll look at how like we can get this lexicographically smallest thing and all, but right now the most important thing is that if you are making the stream like this thing on the go, and you have this block of A's, and then you started a block of B's, then you started a block of C's, then you started a block of D's. When you're considering this character, it has only two choices: either extend this block of D's or start a new block of itself, like with some new character, say E. But these blocks, like this block of A's, block of B's, and block of C's, they don't have any influence on what this character is going to be. All right. I hope someone else is exposing the element. All right. So they like, that's the like core idea. What you can sort of try to do is, what we can try to do is we can try to maintain the last block which we had running, like for each block. So now what can these blocks be? So you could have a block of A, B, C, D, all the way up to Z. So you can have a block of characters, like these are all the possible characters that there can be in the string. So now you can say, what if the last block I was having was had all A's? What if the last block I was having had all B's, and something like that? And you can sort of try to maintain a state for each of these things and try to extend it. And our problem basically says that as long as you try to do that, only the last block matters, and the blocks prior to this, they don't, like they sort of don't matter as long as they follow the condition that each of them has size greater than equal to 3. Then they are all good, and you can just focus on how will this new character interact with this last block. All right. Now, if you forget about the lexicographically string thing for once, and let's just say that we are trying to construct our string, and say we have some string. Let's take the CDC example. All right. Say that you converted the first three to either CCC or DDT. This, but okay. So your first character is C. You let it be C. Then your next character is C. Your next character is D. Your current block has only a single C. All right. What can you do with this D? Can you have D start a new block? Can you just say that, okay, I'm done over here with this block and I'm going to start a new block of D's? You can't do that, because if you do that, there's going to be this block which has only one character. So you need at least 3 characters in each block. So you need to extend this block to have another C. Then you get a new C, and then you extend this to have another C. Now at this point, this block has 3 Cs. At this point, you have a choice. When the new D comes, you have two choices. Either you continue this block, so you have a block of 4 Cs, or D starts its new block. Now, in this problem, since this was like the last D, so you basically had to take this choice. So you would make a block of 4 Cs. But let's just say that our string was something like all Ds after this thing. Then it would be more cost effective to have like start a block of new Ds. So basically, as long as the string has like, if your last block, if your last block, that guy has a size of less than 3, in that case you have to compulsorily extend it with same character. Else you have two choices. Extend it with the same character. If it's a block of C's, then add one more C into it. Or what you can do is start a new block, with a new character. All right. Now, this would be a very good approach if the only thing you had to find was what is the minimum cost I needed. In that case, what you could say is you could start your like DP. You could make your DP array like DP of I, and then this is your character, and this is your some count. Like we have one character over here, like the last block has character of 1. So basically, what you could say is, okay, DP of I is basically I'm at this index I. Character means that this is the character, like the last block is of these characters, all A's, all B's, or all C's, or 1, 2, or 3 would indicate, okay, the last block has exactly one character, exactly 2 characters, and 3 and more characters, something like this. And then you could just basically iterate over all these things, update the next states, and at the end you would have some form of answer. You would again have to have some type checking to see that the last block has at least 3 characters, but you could just get your answer from the last basically DP state. Now the problem over here is you don't just have to find the minimum cost, you also have to find the lexicographically smallest string. All right. So if it was all just about finding the minimum cost to convert a caption into a good caption, this observation itself would have sufficed, that you for every block you have a choice. For like every new character you have a choice. You can either extend the previous block or start a new block. The option of starting a new block only comes when the previous block has size at least 3. In that case, it can become an independent block of its own, and you can start a new block. Then you could basically maintain this DP state that, okay, at each place, like what are the characters that a block can have? It can either have all A's, all B's, all C's, or up to all Z's. And the number of characters it can have is 1 character, 2 character, or 3 or more character. And on this, you could define your transitions. If like this block has 1 character, then you could have this goes to 2 character block, this goes to 3 character block. And if a block has three or more character, it either remains at 3 or more characters or something else, and the new character would have 1 like character, like the new block would have 1 character. Now we want a lexicographically smaller string, and we somehow can use this idea to generate this string. The question is, how do you do this thing? No, 3 won't be convenient. Change the first two, yes, when we're done with the last block. 3 won't be consecutive. I'm not sure what you're seeing. All right, if there's anything, just post it there. Now, so that would have worked for like if we just wanted to have one number which said what is the minimum cost, but we need what is basically the smallest string. So we basically need to construct that string. How do we do that? Like, how do we construct that string? Now there's something called backlinks. All right. So this is like, this concept is basically that in DP, like in dynamic programming, what are you doing in dynamic programming? So you have this state S1, and you have this transition from S1 to S2, and like you basically have these multiple options. You can go from S1 to S2. From S2 you can go to some S4, some S3 over here, some S5 over here. And in a sort of way, when we apply dynamic programming, it's kind of a directed acyclic graph. Like in whichever you apply, like you could either apply it recursively or iteratively, whatever you do, you're sort of you sort of have this directed acyclic graph, and you're just kind of evaluating this thing, this thing. Then you come to this node and say, okay, can I go to this? If I go to this node, then what is the cost I have? Let's just say this is C1. Then if I go to this node, what is the cost I have? This is C2, this is C3, this is C4. And then for each of the nodes, you basically take the minimum cost that you could have under all the choices, and then calculate this guy. And then again, you come back one step and just calculate like the minimum of these guys. That's your normal DP. And that works when you just need the values on these nodes. Now, basically what we are saying over here is we also want to construct the string. So what does constructing the string look like? Now, these states are basically like your choices that you have. So at each edge, at each node, like at each DP state, like at each index, you have a choice that do you start a new block or you don't start a new block. What we do is in DP, in backlinks, like when we maintain backlinks, we say that, okay, I had these two choices and the minimum answer that I got was say a 2. Aside from this 2, we also maintain what was the choice that gave us this answer of 2. So if this was the choice that gave us the answer of 2, we maintain this link, like, okay, this was the choice that gave us an answer of 2, and we call this thing a backlink. So backlink is sort of that things that in DP, whenever you are making a choices, whenever you say that I have all these choices and the minimum of this is my value right now, we take that, okay, what is that minimum which is giving us this value, and that basically allows us to have these backlinks. And what you can do is you can maintain these backlinks all over the place. So let's just say this guy got his best answer from here, and you got your best answer from here after considering all these things. Then once you have your best answer, you can just iterate over your backlinks to see what are the choices that you made. And this iteration would allow you to get your answer. Now, this was the backlink concepts at a very high level. In our problem, what would this entail? Like what would you do with this thing? The first thing is that you want to minimize your string. So like you want to have a lexicographically minimum string. So first, instead of iterating from start to end, let's iterate from end to start. Why do you want to do that? Because when you iterate from start to end, if you fix your C over here, that's actually problematic, because you could also have fixed A, or you could also have fixed B over here, and they would be like lexicographically smaller than C. So maybe like if you just fix A, your cost would go up very high. So you can't always just say I'm going to fix A. So that won't work. So rather than that, since we want a lexicographically smaller string, what you can do is you can start from the end, from end to start. We go from end to start. Then from the end, you start maintaining different blocks. So we basically like have this DP array, like a similar DP array as this thing. This is DP of I, character, and the count. So that would indicate that you have this DP of I, character, and some count. That would basically now indicate that what's the min cost, what is the minimum cost that to basically make your string as from I to the end, like n minus 1, good. And the last block, like in this good string, the last block has these characters ch with count. So basically dp of I and say a and 2 would mean that your like the string s from I to n minus 1 is good, except the last a's, like except the last block. All the other blocks are good. They have size of at least 3. And the last block has 2a's. Like last block is basically this AA block. Now what you can do is we can once again like basically we can maintain this complete DP thing like for all i's for all characters and 3 counts. So 3 counts would be you could either have it 0, 1, 2 or 1, 2, 3. So count of 1 means block of size 1, count of 2 means 2, count of 3 means you could have either it equal to 3 or greater than equal to 3 also works. Then what you can say is you can iterate from right to left, and at each point you are at point I and you have evaluated all the DP states for this I. So this is any generic state. And what you're going to say is, okay, I have what I need to get the answer from I to all the way back n minus 1. Now we want to evaluate the DP of I minus 1 array. All right. So basically what we are saying is we know what is the minimum operations that we need to divide this thing into blocks of size at least 3 except the last block, and we want to do that thing once again for I minus 1. How would the updates look? So if you're at I and the last block is of these characters and it has 1 or 2 characters, like the last block has size of 1 or 2, then for I minus 1 the only choice you have is you extend this thing to have at least 3 characters. Else if you're at I, your last block has these characters and it has 3, like basically 3 characters, at least 3 characters, then you could either extend this guy or you can start a new block of some new character and that would have a size of 1. So you have these two choices. You can calculate the sort of what you could say the cost for this thing. Like the cost for this thing would be your absolute value of s of I minus 1 minus whatever this character or new character you have, and you have to add this thing into this DB, and you would basically do this thing. Now other than that, what we will also do is whenever we are updating this I minus 1 character, we'll also see, okay, what was its previous value, what is the new value it will get due to this update. Is its value becoming better? If it's becoming better, then we are going to maintain a backlink to this guy. All right, we are basically saying that we are going to maintain a backlink up to this guy, and if its value remains the same, then you basically can maintain a backlink where the where your final string would be lexicographically smaller. So for example, if you are at this character I block of size 1 and you get over here from I plus 1 B3 and I plus 1 C3 and I plus 1 D3, and let's just say all 3 of these things have same cost and all of them end up over here. So all of these 3 blocks, like even if the last block had 3 Bs, 3 Cs or 3 Ds, all of them had same cost, and in all of these cases you could start a new block with A. In this case you would maintain a backlink to B because you want your final string to be lexicographically smallest. So after A, it's the best choice to have B because B is lexicographically smaller than C and D. So if there are any clashes with regards to cost, then you would prefer the lexicographically smaller character, else you can just go ahead. And so we'll go on calculating our DP in that way. Update would consecutively. Yeah. So yeah, like that would be the basic idea. And finally, when we are done with all the things, you look at the first the DP array at the first place, like basically DP of 0, some character, and count of at least 3. So you want the first guy to have at least size of 3, like the block size should be at least 3, and also you have to initialize it in such a way that the last block has a size of at least 3. So you could set all other things that there would be to infinite, and last block would have size of at least 3. And finally, so you could just iterate over all the possible DP arrays. Like you could iterate over all the possible character choices you have from A to Z, and take the lexicographically smallest one amongst them, like the first character that gives the minimum cost. All right. Then what you can do is, okay, this is the character, this is the count, and we are at I. You add this character to your res, then you go to I plus 1, and basically you have a backlink. Okay, so you use your backlink to go to I plus 1, some other character, some new character, and some new count. Then you once again add your new character to your array. Then once again you traverse your backlink and get something I plus 2, some new character, and some new count. And you go on doing this thing up to n minus 1 times, and finally your backlink would point to nowhere. That's usually represented by a backlink equal to -1. Try to turn them into A, start to reduce cost, then B, and then C, and then so on. Just, well, start from last in the DP. Yeah, I think I don't get the last part where you're saying we turn them into A. All right. Okay. All right. So that was the idea. In the implementation, actually, my implementation seems to have some bug, but I'll still go over what I was doing over here. So sort of instead of DP, like I've merged this two things into one single state. That has made it a bit complicated. But what we do is initially you maintain a DP array of size n minus 2. Why n minus 2? Because if you look at it, the last block always has to be have at least 3 characters. So even though we said that the last block can have one character which can be extended, in the actual array, okay, you could have one block that has at least 2 characters intermediately, that okay, there is some good block after this thing, so this intermediately you could have a good last block. But at the end we have to ensure that the first block, like all blocks have size of at least 3. So at the start what you can do is, okay, take the last block which has size at least 3. So assume that last block has size at least 3, calculate the cost, and then we can start calculating our DP starting from over here. This would basically guarantee that anything else, like we won't end up with something like there are 2 A's, then you have 3 C's and something. So your last block has a size of at least at 2 or 1, something like that. So what we do is we say that, okay, n minus 2, we maintain a size of n minus like DP of size n minus 2. For the last, like n minus 3th index, we say that for the n minus 3th index, so what I've done over here is represent 0 means there's one character, 1 means there's 2 characters, 2 means there's 3 or more characters. For this thing, we say that, okay, DP of n minus 3 and this state, this is the cost. What we are ensuring over here is the last, like the absolute last block, it has all 3 characters same. So you have last block of size at least 3. Then you iterate over n minus 3 to greater than 0. Look at whatever states you have over here. If this state is infinite, then just let it go. I've sort of calculated this previous state thing. So what are previous states? Previous states are, you get what is the character in this state and what is the count in this state. Count equal to 2 means there are 3 or more characters in this block. If there are 3 or more characters, then you can either continue this block, that is the current state. The previous state would again become equal to current state, or you could iterate over all other characters and have them as like start a new block with them. So that would be your option if you had 3 or more characters in the current block. If not, you just had to like extend this block, that would be like state plus 1. You could do that, and once you had these things, like you calculate your cost and like this would be your cost. And finally you just see, okay, is my like the current DP that I have, like the current cost that I have, is it strictly greater than this cost? If it is, then update the cost and also maintain a backlink to this state. So backlink would be that for I minus one, for index I minus one and this state, the cost that I am getting, that basically comes by traversing to the next index with this state. And finally, when calculating your answer, you maintain a string res. Initially, you set your current state to -1, iterate over all the characters, and the first block has to have 3 or more characters, because the like code caption all have at least 3 characters. And see, okay, does this state have like give me a minimum answer? If it is, then you set it to that, and you basically find out the lexicographically smallest state that gives you minimum answer. If it's -1, this I guess won't be triggered unless and until you're, because we have dealt with string size less than 3 over here. So just to be safe, that this won't trigger. Finally, iterate from I equal to 0 to n minus 3. And what you do is, okay, so this is the state we are in right now. According to this state, this is the character, like this is the last block of this state. Push that character and use your backlink to traverse to what would be the state in on the next index. So you would just go to the next state, next state, next state for like n minus 3 times. And then when you're in the final state, you just push according to that, like the character according to that. So that is like the overall code. And I think this like there is some bug in this. So I'll debug that and share the link after this. So yeah, that was it. How would the approach go if we needed to start the DP from start of the caption? So there's something very easy that you could do. If you wanted to start DP from the start of the caption, you could just reverse this thing. All right. Of course, the lexicographically smaller part, you still shouldn't you start the first loop from n minus 4. The first loop from n minus 4. No, actually, what we are doing is we are using the ith state to update the previous state. So it would still be from n minus 3. As the last bug is being not exactly excluded. So basically what we are doing is we are in my code, we are sort of saying that, okay, this is the last block of size 3. And we calculate the cost for that last block of size 3. And then use that cost to, okay, what if I extend this block? So what can be the previous characters previous to this block? And then we basically go on updating this thing. So what we do is, this is n minus 3, and we say, okay, a block of size 3, what are the different costs for A, B, C, all the way up to Z? Then for A, so this is n minus 4. So when I equal to n minus 3, we come to A, okay, I have a block of size 3 at of all A's. What are the different choices I have? Either extend this thing, so update this DP of n minus 4, A and 2, or start a new block of B's, update this n minus 4, B and 0, or update this n minus 4, C and 0, and so on. So that's like what I've tried to do over here. That would be it. About like what would you do if you wanted to have the DP from start? So something you could do is you could just say that, like, instead of having the loop from back to end to start, you could just reverse this thing and sort of have the whole logic implemented in similar fashion. That would, once again, like, the only plus point you would get over here is that you're iterating from 0 to n minus 1, so it's more familiar. So that's usually what we have to do than iterating from back to front. So that's like more familiar. All right, so there are no doubts. Yeah, so that was the fourth problem. Unfortunately, my code seems to have some bugs, so I'll debug it and share it as soon as possible. So I hope this session was useful, and yeah, and also do check out the new CP31 sheet. it has a lot of new problems added, and also the UI has been changed to some extent. Yeah.